Ciao.
Ciao Cinzia.
Okay, now it is. Thanks. Yes. And in analogy, I want to take some time today to discuss how we can what a similar result is in the functions, holomorphic functions, to show the state that I called B last time. So it's our functions holomorphic in the unit disk. We go for the unit disk itself. Okay. So what are the possible zeros of such functions? And last time we saw finite Blasky products, which are functions which have zeros on a prescribed finite sequence of points. So the point is that we can exploit these results about convergence of infinite products to construct some infinite version of Blasky products, which have zeros on sequences which are not arbitrary this time, but they satisfy some kind of condition. So this is the idea of what I will discuss. So recall that a finite Blasky product is a function of this form. So it's some unimodular scalar times the product, finite products of automorphisms of the unit disk. Which is defined in the unit disk, and it maps the unit disk to itself. And the problem is if I let this n go to infinity, when do I have convergence and which sense I have convergence? So I will recall you. Let me first write the main theorem about convergence of Blasky products. So now, suppose that we have a sequence of points inside the unit disk. And it can happen, two things can happen. So first, if the series converges, then the infinite product. So here I would like to put the automorphisms of the unit disk factors. But it turns out that it's best if I correct with some unimodular scalar. So this unimodular scalar is chosen in such a way such that the value at the origin of each of these automorphisms is positive. That's the logic in which I pick this scalar.
This way it's negative.
If I put 0, I have minus times minus.
Oh, there is a minus, okay.
There is a minus. Ah, sorry.
Okay.
Let me write it. This is part. This is the unimodular factor which I use to correct, and this is the product of the automorphism. So this infinite product converges absolutely uniformly in compacts the function v. So this function obviously will be called the infinite Lasker product associated with the sequence, and the point is that so this function e has a 0 of order m at some point, if and only if m of the AKs are equal to 0. So the zeros, so this is in particular, it's a non-zero homomorphic function, a non-trivial homomorphic function, which vanishes exactly on the sequence AK, and the order of the zeros at each of these points AK is exactly equal to the number of the point AK is repeated in the sequence. And in the contrary, if this condition is not satisfied, then there is no hope to make this thing converge in the sense that even if I take the absolute value here, which is something something bigger, so this converges to 0 locally uniformly formed. Okay. So I cannot choose any factor for unimodular correction factor which can make this thing converge at some non-trivial holomorphic function. Okay. So the moral of this is that if I want to use Lasker products to construct functions with vanish on prescribed sequences, the best thing I can do is assume this condition.
The sum is infinite.
Is infinite, yes. And the proof is quite straightforward if we use the tools that we saw last time about infinite product. So let me remind you that one of the basic theorems about infinite products. So if I have an omega open connected, some domain omega, and then I have a sequence of holomorphic functions in omega. Then this product converges absolutely and uniformly on complex if, so let me, I had it with class 1 here. So if the theory without the theory this function -1 converges in the same case. And in this case, the zeros of the zeros of the function to which this product converges are exactly the zeros of these factors counted with multiplicity. So let's say that this is some function. I want to use this theorem. So I will not write this part, but probably you remember that then the zeros of the infinite product are exactly the zeros of these factors bounded with a multiplicity. And using this theorem, I can prove the first part. So I will leave there the definition of infinite plastic products. And I can prove it here. Okay, so what I do is I take this thing and I just write it in this form. So I have these are my functions at n. Okay, let's say this notation. And I need some kind of estimate for the modulus of k. So I compute k z is equal. I have minus modulus. And here I have -1, which is minus 8k plus modulus of x squared z. And then I have okay. So here let's see. I can take out the common factor from this two guys and the common factor from these two guys. So I get if I take z modulus of 8k from these ones. One, and here I get the same thing. So I can factorize the thing. I get one, two, plus. Yes. Yes. And now you can see that, okay, here I have the term that I like because I know that this series converges. And everything else I can bound by some uniform constant if Z belongs to some compact subset of the unities. So at this point, assume that Z has modulus less than rho, which is 50 less than 1. That's the modulus of N of Z will be less or equal than 1 minus modulus of the AK, because like this is the negative number. Here by the triangular inequality in the fact that everything lies inside the unit disk, I can bound this by 2. And maybe it's easier if I take also AK inside here. Still, this thing is bounded by 2 because this is unimodular and this Z lies inside the unit disk. And below here, I can do the triangle inequality, the reverse one. can still bound the modulus of AK by 1. And the modulus of Z by rho. So I bounded the modulus of the functions f and z by 1 minus AK times some universal constant in this smaller disk. And hence, by, if you want, by the Weierstrass-Sem test, the series of the functions fn converges absolutely and uniformly on this disk. And since rho was arbitrary, it converges absolutely and uniformly on compact subsets of the unit disk. And then the theorem does the rest for us, because it tells us that this infinite product converges to some holomorphic function in the unit disk, and then if this holomorphic function has a zero, it must be a zero of one of its factors. Okay. And the holomorphic functions have only zeros at the points A3. And this solves this. Yes, and this finishes the first part of the right. The second part is, the second part is less important in application, because it says that you cannot do something, but it's I think it's important to know that you cannot do any better in this way. Then afterwards, we'll see that in fact it's not casual that we cannot do better than this condition, because in some sense this condition is the best possible. Anyhow, so for the second part, I just so this is straightforward computation. I wanted to prove that this equals to 0 uniformly compact sets. And again, I use this identity. It's very convenient of it. So I, instead of estimating this, I estimate 1 minus the modulus of this square. Okay. Which did the computation the other time, it can be written as 1 minus modulus of 8k squared times, well, the modulus of z squared divided by yes, and now we want to bounce this from above, so we would like to bound this from below. So from below, this is greater or equal than so to bound it from below, this denominator, the maximum it can be is 1 plus 1, 2 squared. So the denominator is at -4. And if we are in a compact set, so if we assume that the modulus, again, the modulus of z is less than equal to some rho, this part, the minimum it can be is 1 minus rho squared. Okay. And then Then what I wanted to estimate was this thing. Okay. So I put the logarithm in the front, and it becomes the sum. It becomes the exponential of the sum of the logarithm. But here everything is positive real, so logarithms is just real value logarithm. I wanted the square, so I put the square here, maintained by 1/2 there. Sorry, where did I put the logarithm? I put the exponential there. Sorry, without the logarithm there. And this is the exponential 1/2. And then I write what I have there. This is the sum 1/10. The logarithm of 1 minus 5. Here I can use the elementary inequality for the logarithm, which obviously get this one is the right one. The logarithm of 1 minus x is less or equal than minus x. I use this inequality here. So this is less or equal than the exponential 1/2 of the sum. And here I just put the second part with a minus. Then I use the estimate that I proved. So I have a minus, I have an estimate below, which becomes an estimate from above. And it's so equal to minus 1/2. And I have the sum of and so everything is a constant times the partial sum of this series. So I know that my function is uniformly less or equal than a constant which tends to 0 as n goes to infinity, because as n goes to infinity, this sum here goes to infinity, raised something. With a minus, it goes to minus infinity and then exponential minus. So I bounded my function uniformly on this disk by some constant which vanishes, and by definition, this means that it converges uniformly on this disk to the 0 function. Okay. And this proves also the second part of the theory. So up to this point, we know that if we are given a sequence which satisfies this condition, which we will call the Blaschke condition, then I can construct a holomorphic function which maps the disk to itself, and it vanishes exactly at this point. And the natural question is if I can do any better, if, as in the Euclidean case, given any sequence, I can find self-map of the unit disk which vanishes in this sequence. Okay. The answer is no. The answer is that this condition is necessary and sufficient, but it requires some work to show it. In particular, it requires an inequality which is called Jensen's inequality, and this is what we will prove now. So just some another remark. Here, implicitly, I assume maybe that AK are different from zero, like because they divide way. But you can, of course, you can add any order of, you can add a zero of any order at zero. So when I say infinite basket product, what I will mean in general is going to be maybe some unimodular constant times z to the r, some order of zero at the origin times a product of this form. And of course, this condition does not really change if you consider AK to be zero, because you only add R at the total sum. So this, when I say infinite plastic product, this is the most, this is the thing I will refer to. Okay. So you can have a zero also the other. And so yeah, and we would like to prove that this thing is sharp. So you cannot, if this condition fails, there is no function. So we would like to prove so. And this is a good point to expand a little bit the domain of functions that we consider, because if a function vanishes on this form and it's homomorphic from the disk to itself, then any scalar multiple of this function has the same property. So in fact, I can, if I prove this, I can prove that there is no bounded holomorphic function which vanishes on these points. And this space of this now becomes a linear space. So it is then because that what this means is that this is bounded by one, so it does not change if I multiply by a scalar. And this space of bounded holomorphic function, which I will call its infinity of the disk, has a linear structure. And the Banach space, and it is a Banach space with the norm, with the suit norm. Okay. So from now on, we will almost exclusively consider bounded holomorphic functions because of this Banach space property. Okay, but going back to this, on how to prove the thing, we need what I said, yeah, what I call Jensen's formula or Jensen's inequality. So Jensen's formula. Let me write it and then I will comment it. It says take F holomorphic, let's say in the D, or holomorphic in some disk. And I want it holomorphic in the closure of the disk, which means that I can extend it holomorphically in an open set which contains this compact disk, centered at the origin. Then, if assuming calculus of generality that it does not minus at 0, then I can write the integral to the mean value of the logarithm of the modulus of the function on the boundary of this disk as so this is the value of the logarithm of f at 0. So if I were to stop here, this would mean that with respect to the point 0, it satisfies the mean value property of this function ln of f. But what is actually true is that it doesn't satisfy the mean value property, but you have to correct it some factor, which depends only on the zeros. So AK is where this AK is smaller than rho. Yes. So yes, as I was saying, it says that it does not satisfy the mean value property at the origin of this function, but it satisfies a sub mean value property in the sense that this is a positive number, so this is less than the mean value of the boundary, and the correction factor is exactly this finite sum, which only depends on the zeros of the function. So the formula is exactly true as I write it, but we will prove an epsilon weaker version, which is a bit easier to prove. So we will assume that f does not minus on the circle with center 0 and radius r. So as I said, the formula is true even if the function vanishes on that circle. But then you have to be a little bit careful with the matters of convergence and integral, and it's a good exercise. I mean, it's not something deep. Exercise starting from this statement where you assume that f does not minus on the circle to pass to the general one where f might minus on the circle. Not also that here, if I assume that f might have zeros on the circle, it does not really make any difference if it's less or equal because this logarithm vanishes for points which are exactly in the circle. Okay, let's make the picture. We have our circle This is the point, 0. F is holomorphic in a slightly bigger domain. Okay. And it has some zeros. And then I take the mean value of the logarithm of this circle. I only consider the zeros which lie inside, of course, according to multiplicity always. And then I have this this expression for the value of the polynomial. Okay. So maybe I will start the proof after the break. Okay. So we divide into cases the proof. One is the easiest one where it can happen that F does not have any zeros inside this closed disk. Okay. So we are in a situation like this. Then what we have to prove? Yeah, I did. Then in fact this sum is empty, so we have to prove that we have the mean value problem. And so let's add something. Closed disk. Then it does not vanish in some neighborhood of the closed disk. So I can find some neighborhood. Omega in which set does not vanish. And now omega is often connected. Okay. I have a domain on which a holomorphic function does not vanish, so I can find the holomorphic logarithm of that. So there exists D, which was proved by Nicola actually next year. Holomorphic in omega such that e to the d, you know, and so morally the g is the log is right. And so now this formula looks very convincing because it's actually just the mean value property for harmonic functions, which are real parts of holomorphic functions. And this is the idea of the proof. So in this case, I can write G as U times D. So U plus I times D. These are harmonic functions. And so U is the real. This is what we're interested in. And by taking the modulus of this equation, I see that the modulus of E to the D, which is just the E to the real part of D, which is E to the U. This is the modulus of that. So in particular, U is the logarithm of the modulus of F in omega. Well, remember this thing does not vanish, so this is well defined, does not have any singularity. And then I just write I can can do it in many ways. I can just invoke the mean value property for harmonic functions, but I can, let me do it with the Cauchy formula for function. So write the Cauchy integral to 0, 0. So 0, 0 is 1 over 2 I. The integral on the circle modulus for z equals 0. G which is a parameterized circle. To find G and then d zeta, which is I rho divided by I cancel this quantity. I was nuts, and I get, of course, the mean value formula. And by taking real parts, I find that u of 0 is the mean value. But u was just the modulus of the logarithm of the modulus. Yes. So in fact, you see from the proof that when the function f does not vanish in the domain, then the logarithm of the modulus of f is a harmonic function because it's the real part of an analytic function. And this just says that the harmonic function satisfies the mean value property at priori. Whether when I have some zeros, so case 2 now. So f 1, 2, A1. When I say it vanishes at this point, I mean that it vanishes exactly at this point, and the order of the zero path at AI is I repeat, AI as many times as the order of the zero path at point. Then I can reduce the problem to the previous case, and to do that, I have to construct a function which does not vanish on the closed list. And to do that, I just divide by a function which vanishes on these points, which I know how to construct. I consider a finite class topology. So since I can only have a finite number of zeros inside this closed unities, I don't need to use infinite class products. I can only divide by a finite class product. want to reduce the problem. In case one, consider the finite line. Okay, capital F is F divided by this. Okay, so I have divided out all zeros of F. Sorry. I have to be more careful because I work in a disk of radius rho, not the disk of radius 1. So it's better, yeah. It's, so I have to so I want the function with its values exactly at the points no. And so if I consider
You can replace the Z by Z to the row.
yes.
And A by A to the row.
Yeah, you can, so I scale everything like
Post A.
so if I do this, and yet, so yeah. Yes, see, because here I had scaled only one of the two, and I realized that it's problematic. But here it should be okay. So this function, so let's call this tilde, and let's say beta is the classical. So this function is at AK, and at the circle of radius R, at the circle of radius rho, Z over rho is of modulus 1. So, yes. So the modulus of beta is 1, and the modulus of zeta is rho, because when the modulus of zeta is rho, the modulus of this quotient is 1, and the finite elastic product is modulus 1 of this. Yes. Okay, so now I divide f by this function. And I don't have any zeros inside the closed unit disk. So here I assume that these zeros are inside the open unit disk because I work with the a priori assumption that f does not vanish in the circle. So this in the closed disk of radius rho. Yes. It is holomorphic in the closed unit disk because F is holomorphic in the closed unit disk by assumption. And beta is holomorphic in a disk of radius rho plus epsilon. Okay. So it's holomorphic in a bigger open set. So I can apply the case number one, because I know that for such functions, the integral 0 to pi of n is exactly equal to the logarithm of the absolute value of the order. But the point is that as the way that I chose beta, that Nicola helped me choose beta, is that it vanishes in the circle. Okay. So in fact, this factor here is 1. And so maybe I want to erase the formula for beta integral. So this beta is really not here. I can forget it. And I get that the integral from 0 to pi ln beta is equal to ln of 0 minus ln of beta 0. But this is the ln of this product. So if I put delta equals to 0, I get minus k divided by square. This all goes away. And I get the sum on to n of ln of k divided by rho. Here I have it with the minus, so it becomes the ln of rho divided by modulus of k. And this concludes the proof. As I said, you can try to do it as an exercise to prove that even if you have some zeros in the circle, they do not really matter. You can include them or not include them. Same. So as I said, the motivation for introducing this gentle formula was to understand the zeros of functions which are bounded in the unit disk. And you can see that something close to that is happening here, because I can relate a sum of involving the zeros of the function to some integral of the function on a circle. So this suggests that there must be some relation between how many zeros you can have, so how large this can be, to how fast the average growth of f it is. Okay, and this can be made precise, and it's the next proposition. it's this proposition. Let's use these notations. Logarithm plus of x is that's the positive part of the logarithm. So suppose that f is polymorphic with the units. And this quantity, so you can take, so this is very reminiscent of what appears in the Denton formula. I take the soup over all R of the positive logarithm of f. And suppose that this thing is some finite quantity, which I will call it this way, but it does not really matter, it's some finite quantity. And suppose that A1, A2, it's a countable sequence of zeros that have counted according to multiplicity. Then they satisfy the Glassky condition. So this something like we wanted to prove it for bounded functions, but in fact we proved it for functions which satisfy this condition. It might not be clear if this is for sure. This proves it also for bounded functions because Ln plus is a monotone function if the function f is bounded by m. So remark. Then Ln plus of f is bounded by and in particular this supremum is finite. So for sure we prove it for bounded functions. We prove that any bounded function it has zeros which satisfy the Glassky condition. And at this point it's not really clear if we prove it for any larger class. Maybe it's going to be useful later. In particular, I use this notation norm of f index n because it can be proven that this is a larger class, which is called Nevalina class and so on, but I will not enter into that. At this point, we're interested also for bounded functions. And this proves that this Glassky condition is true. You can have a function f bounded in the unit disk, which has zero exactly at the points ai, if and only if they satisfy the Glassky condition. Because if they satisfy it, I can construct it. Is the Glassky product, infinite Glassky product associated with the sequence. For a generic function, I saw that this condition is also necessary. And the proof is not difficult, assuming we so now that we have the Jensen's formula. Okay. So we prove density formula only in the case where the function does not vanish from the circle where you apply it. So we have to be a bit more careful using our radius. So suppose this is the unit list now. And here are the points where the function f vanishes. This is for sure a countable set, which can only accumulate on the circle. So the modulus of AK must go to 1 because where the identity principle, a homomorphic function cannot vanish on the set which accumulates inside the unit list. Okay. So I can find just by confronting cardinalities. The sequence of radii I can find circles which simply do not intersect any point of the sequence and they tend to the boundary. So Rn is some sequence of radii smaller than 1, increasing. And Rn equal to 1. I can pick, for example, this circle, I can circle passing here. And just because these circles are unfoundedly infinite, the points are unfoundedly infinite. And on this circle, I can apply Densis formula. Yes, and I can also assume also we can't plot the f of 0 is not equal to 0. If f of 0 is equal to 0, then just divide out the 0 at the origin by some z to the r, and then apply the same argument to f divided by the so Jensen's formula tells us that the logarithm of modulus of f of 0 plus I just like this. N. Okay. The right hand side is just smaller than what I get if I replace with the logarithm plus of the modulus of f. And by assumption, this quantity is uniformly bounded in R. And this is smaller than this one. This is fine. That was our assumption. What happens here? What happens here is that.
Yeah, the sum is not exactly infinite, right?
Yeah, it's not infinite, so it's only for a it's smaller than Rn. But that's what I wanted to say now. You can rewrite it. So you can just play around with the symbolism, in fact, and you say, okay, I can sum up to infinity. To the left side. is I can sum up to infinity, but then I take the Ln plus. Okay? Because what is done is that, okay, if your AK has norm less than Rn, this quotient is bigger than 1, so it's just a normal logarithm. If my AK has modulus bigger than Rn, then this quotient is less than 1, so the logarithm is negative and this is 0. Everything is 0. So I just derive it in this way. But now I'm done because I can just take the limit of n goes to infinity. Of this thing. And this is a monotone family, positive monotone family functions. I can use the monotone convergence theorem to say that this converges, in fact, the sum of this thing converges to the sum of the pointwise limits of this thing. But the pointwise limit is just ln plus 1 over modulus of AK, but every AK is inside the unit disk, so I can forget the plus here because this thing is always bigger than 1. I took the limit in the left, but this was less or equal than uniformly bounded. And so this term converges, and this is now you can do a calculus exercise to show that this implies exactly that the other term converges because 1 minus x is less or equal than the logarithm of 1 over x. So the sum that we want to control is less or equal than this. And this will be the sum converges. And this is yeah. So if I have so this characterizes completely the zeros of bounded polymorphic functions in the unit of this. And as we did with Weierstrass theorem, that it was very useful then to prove an interpolation theorem, you can also use these ideas to prove an interpolation theorem for bounded polymorphic functions in the unit list. So this is Carlson's theorem. This is what the proof that I will do tomorrow. But let me just start with warm up for this theorem of Carlson without any heavy calculations or whatever. The Lasky products, I don't know which was the first time that they were considered infinite Lasky products. They were before Berlin, before maybe 20. On the vanilla,
Sorry, may I ask a question?
Yes.
You have already erased, but there was a limit for n going to infinity of something, but I don't see the n in the second, maybe. Where was the n in the function?
So there was a constant term from Identity formula. And then you had and then I guess this is what you mean, Rn divided by 8. 8 and 1, 2.
Ah, okay, is Rn and AK, okay.
Yeah. Rn is the radius which tends to 1. And
Okay.
here I find the Morton convergence theorem, but the limit inside.
Thank you very much.
Yeah. In fact, the problem as stated for entire functions is already so given some points. Given points that n is a disk and doubling n. Decide if there exists a function from the disk itself holomorphic. Which interpolates this data. So stated like this, it's really even if it's for infinite sequences, it's really a corollary of fixed interpolation theorem to prove that the necessary and sufficient condition is again the positivity of the corresponding quadratic form. So this is if and only if by fixed finite interpolation. If and only if this matrix this matrix is positive semi-definite, so which is exactly the positivity of the quadratic form condition, meaning an infinite matrix being positive, meaning that every finite section of this matrix is positive semi-definite. That is because in for functions from the discretes to itself, you can use normal families, and from a finite interpolation problem pass directly to an infinite interpolation problem by normal family. Maybe it's something I can show you how you can do it if you want. The point I want to make here is that this problem, fixed target, fixed points, find if there exists a function, is already solved. Okay. So Carlson asks a different problem, which is much more, it's much deeper, I would say. So, the visual in 68. Fixed. So I fixed on the places where I want to interpolate. And then I want to decide if for every sequence of data, so if I ask for every sequence of points in the unit disk to find an interpolating function in the disk itself, it's 2 months for every So if I ask that for every sequence of points in the disk, I can find the function of the disk itself and solve this interpolation problem, it's too much. This cannot be done. But it makes sense if I ask for every data with sufficiently small L infinity norm. So for every data such that the modulus of Wm is smaller than some epsilon. So problem ask this problem. Ask this question. If I had a sequence of points in the disk, decide if for every data Wn of sufficiently small L infinity norm, so sufficiently close to the origin, I can find the function from the disk to itself which solve this interpolation problem. Now, this is a problem which only depends on Zn, right? Because there is a quantifier in front of Wn. So this is a yes or no problem which only depends on the initial sequence Zn. And in fact, it's much more convenient to reformulate this problem in terms of H infinity bounded analytic functions. So this is equivalent to say that for every Wm in L infinity, I can find f bounded analytic function such that f of Zn equals Wm. This is Patterson problem. Fix that n if for every bounded sequence you can find the holomorphic function bounded in this. And in this problem, it's not even clear that there exists some Zn which satisfy this property, because I'm allowed to change the target values, and I still have to be able to find an interpolating function. Okay. But Carlson's theory tells us that there exist such sequences, many of them, and gives a complete geometric characterization of such sequences that for which this problem has a positive use. So I think it's better if we are not entering into the details of Carlson's theorem. And, yeah, the proof that we will discuss tomorrow is not the original proof of Carlson, but it's a version, so it's a re-elaborated version of the proof of Peter Jones. Okay.
We take that by some open.
Yes. Because here I have a quantitative thing. Yes. So to go from here to here is it's trivial. To go back, you need I think it's not. Okay, let's see. Let's make it more precise. So one, two. If I have Wn which are bounded by M, then the epsilon, so I can find F from the unit such that F of the M, so this is by one. F of the And so then the function and theta and over epsilon f is a bounded holomorphic function which interpolates the data. Going by 2 to 1, going by 2 to 1 means that so suppose Wn is less than epsilon. Then we can find bounded. Yes, you need the open I'm thinking if the open mapping theorem is enough, or you need the linear interpolation operator. So let's use the open mapping theorem. Yeah, so you're right, going from 2 to 1, it requires some functional analysis. And the point is that in 2, you have this operator restriction which goes from H infinity to L infinity. And takes the function f and restricts it against device. And what this property 2 says is that R is subjective. So R is subjective, R is linear, and it's also bounded because if I take some bounded holomorphic function Rf, with this the sequence f of the n, then the modulus of f is of course less or equal than the supreme norm of f. And if I take a sub here, this is the infinity norm, it's a conversion. And since it's a linear bounded subjective operator, I know that for every, from the open mapping theorem, for every, there exists some constant C positive, such that for every W and in an infinity, I can find an F in H infinity of such that the norm of F in H infinity is less than C times the norm of W in L infinity. And R of F is W1. And R is Wn, but Rf is by definition F of Wn. Okay, and this gives this statement, because then I can divide the norm of F by C to get that if Wn is less than epsilon over C, then F must be this to itself. Yeah, so you require some function analysis I didn't realize before.
Sorry, you are following the proof of Peter. Can you write the name at the blackboard?
Yes, the proof that I will do tomorrow.
Yeah.
So there was an original proof of Carlson from 58. Then there was a proof of Peter Jones. I will write it now.
Okay, thank you.
Carlson. Then there was a proof of Peter Jones. I don't remember when exactly. And the proof that I will follow is of Vinograd, Gorin, and Joseph. Yes. And it's from 81, and it's heavily based on the proof of Peter Jones. In fact, Peter Jones has an argument to come up with some certain functions that we will see tomorrow. And they say that if you can guess beforehand which are these right functions, then you can even furthermore simplify the proof of Peter Jones. And this is a very clean proof that fits in one page, but it's based on the fact that you can guess the right functions by the proof of Peter Jones. I will do the proof tomorrow.
Sorry, another question. In the last line of second blackboard, is the norm of W, the last term is norm?
Yeah, so I'm saying that from the open.
Which kind of norm is this of W?
L-infinity.
What?
L-infinity, so supreme.
L-infinity.
Yeah.
Okay, thank you.
Yeah.
It was not clear from the blackboard.
Yeah.
Thank you.
So this is the open mapping theorem, which tells you that if you have a bounded linear surjective operator from a Banach space X to Y in general, then you can always find the pre-image with the control of the norm by some constant.
Thanks.
Okay. Thank you.